Ladies and gentlemen, welcome back to Space Nest. For decades, humanity has looked into the night sky, believing that the rules of the solar system were settled, predictable, and fully understood. We arrogantly assumed that our little corner of the galaxy was a gated community, largely immune to the chaotic traffic of the wider universe. We believed that interstellar visitors were rare, brief, and largely irrelevant to planetary dynamics. But today, that assumption no longer holds because this moment, this confirmation, has changed absolutely everything. Using unprecedented precision, the James Webb Space Telescope, or JWST, has delivered data that forces scientists to pause, recalculate, and in some cases rethink long-standing models of how objects move through our solar neighborhood. This isn't just a minor correction to a spreadsheet. This is a fundamental rewriting of orbital mechanics as we know them. What once appeared to be a distant interstellar wanderer has now revealed a trajectory that aligns disturbingly close to Mars. This object is not behaving like the dumb rocks we have spent the last century cataloging and ignoring. This is not speculation, and this is certainly not guesswork from the fringes of the internet. This is trajectory confirmation based on infrared observation, gravitational modeling, and orbital refinement that was simply impossible before we launched JWST. What makes this moment extraordinary is not just the object itself, but what its specific path tells us about the environment we live in. Interstellar objects are expected to pass through quickly, influenced only weakly by the sun before disappearing forever into the dark. Yet, here we see something fundamentally different unfolding on the monitors. We see a path that responds, adjusts, and bends in ways that demand closer scrutiny from every astronomer on Earth. JWST's instruments track subtle changes in velocity, orientation, and thermal signature that ground-based telescopes would have missed entirely. These are details that reveal how deeply this object is interacting with the gravitational architecture of our solar system. The Mars trajectory confirmation is especially significant because Mars occupies a region that acts as a gravitational crossroads for the inner system. An object passing this close does not merely pass by, it engages with the planetary defense lines of our neighborhood. It exchanges energy, momentum, and information with the system itself, creating a dynamic that we have rarely observed in real time. That means this encounter becomes a natural experiment, one that allows scientists to test models of gravity, material composition, and interstellar dynamics under real conditions rather than simulations. And this is where everything changes for those of us who follow the real science. Because if an interstellar object can enter our system, adjust its path, and align toward a major planetary orbit, then our solar system is not the isolated island we once imagined. It is part of a larger active galactic environment, one where material from other star systems can interact with planets in meaningful ways. We are not living in a bubble, we are living in a busy intersection, and we are just now noticing the traffic. The JWST confirmation also exposes the severe limits of our older, beloved telescopes. Ground-based observations hinted at unusual motion, but the Webb provided the clarity necessary to make a definitive statement. Its infrared vision cut through dust, distance, and uncertainty, allowing scientists to reconstruct the object's past, path, and project its future motion with confidence. This wasn't a lucky snapshot taken by an amateur astronomer in a backyard. It was continuous, data-driven verification that stands up to the harshest peer review. The implications extend far beyond the immediate vicinity of Mars. If this kind of trajectory is possible once, it is statistically certain to be possible again. That means planetary defense strategies, interstellar science, and even the origins of organic material in the solar system must be reconsidered immediately. Objects like this could deliver compounds, trigger atmospheric effects, or reshape orbital environments over astronomical timescales. We have to stop looking at these events as anomalies and start seeing them as features of our galactic geography. Most importantly, this moment represents a massive shift in the scientific mindset. Instead of asking whether interstellar objects matter, we are now asking how often they interact and how deeply they influence planetary systems. We are asking what they can teach us about the galaxy beyond our sun, and the answers might be more complex than we are ready for. This is why this confirmation matters so much to everyone watching this channel. Not because of fear, and not because of wild speculation, but because it proves that discovery is far from over. It proves that the universe is still capable of surprising us in ways that rewrite what we thought we knew about our own backyard. This changed everything, and we are just reading the first page of a new chapter. What truly transformed this moment from curiosity into confirmation was the role played by the JWST, whose capabilities go far beyond anything previously available to astronomers. Earlier observations of interstellar objects relied heavily on reflected visible light, ground-based tracking, and limited windows of observation. These methods often left room for uncertainty, especially when dealing with faint, fast-moving objects entering from beyond the solar system. We were essentially trying to track a speeding bullet in the dark with a disposable camera. In contrast, Webb operates primarily in the infrared spectrum, allowing it to detect heat signatures, surface composition clues, and subtle motion changes that cannot be seen from Earth or older space telescopes. What makes this confirmation so decisive is the absolute level of precision involved in the data collection. Webb did not merely detect the object once or twice during a lucky sweep. It collected consistent data over time, enabling scientists to refine orbital calculations with extraordinary accuracy. By tracking minute shifts in velocity and direction, researchers were able to reconstruct the object's past trajectory and project its future path. These refinements narrowed the margin of error to a degree that effectively eliminated alternative interpretations. The trajectory toward Mars was not an artifact of noisy data or incomplete observation. It emerged repeatedly, independently, and consistently from the measurements, defying the skeptics who wanted to dismiss it as a glitch. Infrared analysis also played a critical role in ruling out simpler, more boring explanations. Variations in brightness that might once have been attributed to observational angle or rotation were instead revealed to be linked to physical and thermal properties of the object itself. We're seeing the physical reality of this visitor, not just a flicker of light. JWST's instruments measured how the object absorbed and re-emitted solar energy, allowing scientists to estimate its size, shape, and surface behavior. These measurements fed directly into gravitational models, improving predictions of how the object responds to planetary influence as it moves inward through the solar system. Another key factor is Webb's vantage point, sitting comfortably at L2. Positioned far from Earth's atmospheric interference, it avoids distortion caused by air, light pollution, and thermal noise. This clean observational environment made it possible to detect extremely subtle gravitational perturbations, tiny deviations in motion caused by planetary bodies. Those deviations, when analyzed over time, reveal the trajectory that aligns with the Mars orbital region in a way that could not be dismissed as coincidence. Without Webb, such small but crucial signals would likely have been lost entirely in the background noise of the cosmos. This confirmation marks a turning point in how astronomers treat interstellar objects. Instead of relying on short observation windows and incomplete datasets, scientists now have the ability to follow these visitors with continuity and depth. Webb transformed what would have been a fleeting astronomical footnote into a data-rich event with planetary significance. The confidence derived from this confirmation is not emotional or speculative. It is mathematical, observational, and repeatable, which makes it impossible to ignore. In essence, the telescope did more than observe an object. It validated a new reality. It closed the gap between uncertainty and understanding. By providing definitive trajectory data, it shifted the conversation from "could this be happening" to "this is happening, and we must understand why." That shift is what truly changed everything for the scientific community. What makes the alignment toward Mars so extraordinary is that it defies the standard behavior scientists expect from interstellar objects. Traditionally, these visitors are thought to enter the solar system on steep hyperbolic paths, briefly influenced by the sun's gravity before continuing onward, never to return. Their trajectories are usually simple: in, curve slightly, and out. But the path observed here tells a very different story, and it is one that keeps researchers awake at night. It suggests a deeper and more prolonged interaction with the inner solar system than we ever thought possible. The alignment toward Mars is not a single point prediction, but the result of refined orbital modeling based on repeated observations. As the object moved closer, its trajectory showed adjustments that cannot be explained by random motion or observational error alone. Instead of maintaining a straight escape path, it exhibited subtle but measurable changes in velocity and direction that bring it into close geometric alignment with the Mars orbital plane. This behavior indicates that the object is responding meaningfully to gravitational influences within the solar system rather than simply passing through unaffected. It is almost as if the object is feeling the gravity of our planets and reacting to it. Mars plays a critical role in this context because of its specific position in the lineup. Sitting between the inner rocky planets and the outer gas giants, Mars occupies a region where gravitational forces can create complex interactions. An object approaching this zone may experience cumulative perturbations that reshape its path over time. The alignment suggests that the object's trajectory is being shaped not just by the Sun, but by a multi-body gravitational environment in which Mars acts as a significant participant. This challenges the idea that only massive planets like Jupiter can meaningfully alter the course of interstellar visitors. We used to think you needed a gas giant to catch a comet, but Mars is proving us wrong. What deepens the significance is the timing of this entire event. The alignment occurs during a window when Mars is positioned such that even small changes in speed or direction can result in large differences in long-term trajectory. That sensitivity makes the observed path especially notable and raises eyebrows across the community. It implies that the object is not merely brushing past the Mars orbital region, but entering a configuration where planetary gravity could influence its future motion in lasting ways. This raises questions about whether such encounters are more common than previously assumed, and whether they have been overlooked due to limitations in observational technology. How many of these have we missed because we were looking the wrong way? The Mars alignment also forces scientists to reconsider risk assessment and planetary interaction models. While there is no immediate claim of impact, trajectory alignment is the first condition required for any close encounter scenario. Understanding how and why an interstellar object can align with a planetary orbit becomes essential not only for academic curiosity, but for long-term planetary monitoring. Even rare events matter when their consequences could be profound for a planetary surface. Beyond risk, the alignment creates an unprecedented scientific opportunity that we cannot afford to waste. Mars is one of the most closely studied planets in the solar system, with orbiters, landers, and decades of accumulated data. Any interstellar object passing through its orbital neighborhood provides a unique comparative reference, allowing scientists to study how material from another star system behaves in proximity to a well-characterized planet. This transforms the event from a distant observation into a practical experiment in real cosmic conditions. Ultimately, the unexpected alignment toward Mars reframes how scientists view interstellar objects altogether. Instead of treating them as distant curiosities with fleeting relevance, this trajectory suggests they can engage with planetary systems in structured, measurable ways. That realization alone reshapes our understanding of the dynamic relationship between our solar system and the wider galaxy. For a long time, interstellar objects were treated as astronomical anomalies, rare visitors that slipped through the solar system too quickly to matter. The prevailing assumption was that they followed simple, predictable paths governed almost entirely by the sun's gravity, with no meaningful interaction with planets and no lasting significance. The events described here directly challenge that framework and expose how incomplete those assumptions were. What was once considered settled science is now clearly open to revision. At the core of this challenge is behavior that does not fit the classical model we learned in school. Instead of displaying a clean one-time flyby trajectory, the object demonstrates changes in motion that require more complex explanations. These deviations force scientists to reconsider how interstellar bodies behave when they encounter a mature planetary system. Rather than acting as passive debris drifting through space, this object appears to engage dynamically with multiple gravitational influences. This suggests that the solar system is far more interactive than previously believed. This discovery also undermines the assumption that interstellar objects are too rare to study systematically. Earlier detections were limited by technology, often identified late and lost quickly as they sped away from the sun. With improved observational tools like JWST, it is becoming clear that such objects may pass through planetary systems more frequently than expected. If that is the case, then prior models underestimated not only their number, but their potential impact on planetary science, orbital dynamics, and even the chemical evolution of solar systems. Another long-held belief being challenged is that planetary systems are largely insulated from their galactic environment. Traditional models portrayed the solar system as a relatively closed structure influenced mainly by internal dynamics. The behavior of this object suggests the opposite is true. It indicates that material from other star systems can enter, interact, and potentially alter planetary environments. This opens the door to new thinking about how solar systems evolve over time and how external material may contribute to planetary development. The implications extend beyond motion alone and touch on the very ingredients of life. If interstellar objects can interact meaningfully with planets, then they may also carry information, chemical, structural, or even isotopic, that reflects conditions in distant star systems. This transforms them from fleeting curiosities into carriers of cosmic data. Studying such objects becomes a way to sample the galaxy without leaving the solar system, offering insights into how common certain materials or formation processes may be elsewhere in the universe. We're getting free samples delivered to our doorstep. Challenging assumptions is rarely comfortable, especially in a field built on precision and long-standing models. But science advances precisely through moments like this, when observations force a re-evaluation of what was once taken for granted. The object's behavior does not invalidate prior knowledge, but it certainly complicates it. Instead, it reveals that earlier models were incomplete, shaped by technological limitations rather than fundamental truth. By confronting these assumptions, scientists are now compelled to expand their theories, refine simulations, and design future missions with interstellar interaction in mind. We might need to rethink mission parameters for upcoming projects like JWST or the 3I Atlas updates. This shift marks a transition from viewing interstellar objects as statistical outliers to recognizing them as active participants in cosmic systems. That change in perspective is one of the most profound outcomes of this discovery. It reshapes not just how we interpret one object, but how we understand the solar system's place within the broader galaxy. The reason this event functions as a natural scientific experiment lies in the unique position Mars occupies within the solar system and the depth of knowledge humanity has accumulated about it. Unlike distant gas giants or poorly characterized bodies, Mars has been observed continuously for decades by orbiters, landers, and rovers. Its gravitational field, orbital parameters, atmospheric properties, and surrounding space environment are mapped with exceptional precision. When an interstellar object passes through or near this region, scientists are not observing in the dark. They are measuring change against a well-understood baseline, which is the gold standard in science. Mars sits at a transitional boundary between the inner, rocky planets and the outer, more massive worlds. This location makes it especially sensitive to gravitational interactions that are neither negligible nor overwhelmingly dominant. An interstellar object moving through this zone experiences a complex balance of forces from the Sun and nearby planets, allowing researchers to study how such objects respond to multi-body gravitational systems in real time. Unlike simulations which rely on assumptions and simplifications, this encounter provides direct observational data of physics unfolding naturally. What elevates this from a simple flyby is the predictability of Mars itself. Because its orbit is stable and precisely known, even tiny deviations in an object's trajectory become meaningful. Scientists can isolate whether changes in motion result from gravitational interaction, outgassing, rotational effects, or external forces. Mars acts as a reference point, enabling researchers to test theoretical models with unusually high confidence. In effect, the planet becomes a laboratory instrument on a planetary scale. There is also a temporal advantage that cannot be overlooked. Mars's orbital period and position during the object's passage create a time window in which small forces can produce measurable outcomes. This allows scientists to observe not just where the object is going, but how its path evolves step by step. Such data is invaluable for refining models of orbital mechanics, especially for bodies originating outside the solar system, where initial conditions are often poorly constrained. We are essentially watching a live crash test of our physics models. Beyond motion, the experiment extends to material science and energy exchange. As the object approaches the inner solar system near Mars's orbit, changes in temperature, surface activity, and structural response can be measured. Comparing these responses to Mars's known environmental conditions helps scientists understand how foreign material behaves under solar radiation levels different from those of its home star system. This offers rare insight into the physical nature of interstellar matter under controlled cosmic conditions. The broader significance is that this experiment requires no artificial setup. No probe was launched, no trajectory engineered, and no tax dollars were spent on a launch vehicle. Nature itself arranged the variables: a known planet, a foreign object, and a measurable interaction. Events like this cannot be replicated on demand, which makes their scientific value extraordinarily high. Each data point becomes part of a permanent record that can be reanalyzed as theories improve and new questions arise. In this sense, Mars is not merely a destination or a point of interest. It is a benchmark. Its role in this encounter transforms an unexpected trajectory into an opportunity to validate physics, test assumptions, and deepen understanding of how planetary systems interact with the wider galaxy. Perhaps the most far-reaching consequence of this confirmation is how it reshapes humanity's understanding of the solar system's relationship with the wider galaxy. For generations, the solar system was imagined as a largely self-contained structure. We pictured a stable arrangement of planets and debris shaped almost entirely by the sun's gravity and internal processes. External influence was considered rare, fleeting, and inconsequential. This event disrupts that mental model by showing that the boundary between our system and interstellar space is far more porous than once believed. If an object originating beyond our star system can interact with planetary orbits, and exhibit measurable responses to internal gravitational structures, then the solar system is not isolated at all. It is embedded in a dynamic galactic environment where material, energy, and momentum regularly cross borders we once thought were firm. This realization reframes the solar system as part of a larger ecological network within the Milky Way rather than a closed cosmic island. That shift has deep implications for planetary science and the history of our own Earth. It suggests that planets may have been influenced subtly or dramatically by interstellar visitors throughout their histories. Such objects could have delivered exotic materials, altered orbital paths, or even triggered environmental changes during key stages of planetary evolution. Over billions of years, these interactions, rare individually but significant collectively, may have helped shape atmospheres, surfaces, and chemical inventories in ways not yet fully understood. We might be looking at the delivery mechanism for the building blocks of life. The confirmation also influences how scientists think about planetary defense and long-term planning. While most attention has focused on asteroids and comets native to the solar system, interstellar objects introduce a new category of consideration. Their high velocities, unfamiliar compositions, and unpredictable origins make them fundamentally different. Understanding their behavior is no longer optional curiosity, it is a survival requirement. It becomes part of a comprehensive strategy for monitoring the space environment around Earth and its neighboring planets. We need to know what is out there and where it is going. On a philosophical level, this moment changes how humanity perceives its place in the universe. The realization that matter from distant star systems can pass close to familiar worlds reinforces the idea that cosmic processes are interconnected. The same physical laws govern objects across vast distances, and the galaxy is not a backdrop, but an active participant in shaping planetary systems. This perspective encourages a more holistic approach to astronomy, one that looks outward not just for discovery, but for context. We are starting to see the forest, not just the trees. The reshaping of perspective also affects future exploration priorities. Instead of viewing interstellar objects as rare anomalies, scientists may begin treating them as valuable messengers carrying information from other parts of the galaxy. Studying them becomes a way to extend exploration far beyond the reach of spacecraft, using natural travelers as probes of distant environments. We should be chasing these things, not just watching them. Ultimately, this confirmation expands the narrative of the solar system itself. It is no longer just a local story of planets circling a star, but part of a continuous galactic exchange. Recognizing that reality alters scientific priorities, theoretical frameworks, and humanity's sense of cosmic belonging. Once that perspective shifts, it cannot be reversed. We have seen the truth, and we cannot unsee it. We must also consider the controversial but necessary perspective brought forward by scientists like Avi Loeb. When we see objects with non-gravitational acceleration or strange trajectories, we have to ask if they are natural or artificial. While the data here points to natural phenomena, the very fact that we are having this conversation shows how much the paradigm has shifted. If nature can throw rocks at Mars, could a distant civilization throw a probe? The Enrico Fermi paradox asks, where is everybody? Maybe they are sending automated surveyors that we are just now learning to track. This object might be natural, but it proves that the highway is open. And if the highway is open, anyone or anything can drive on it. We are updating the 3-year atlas of our knowledge in real time. We are watching perihelion passes with a scrutiny we never possessed before. This is a wake-up call for the entire scientific establishment. The universe is not a museum. It is a machine, and the gears are turning right in front of us. Thank you for watching Space Nest. Stay tuned, because the sky is not as empty as they told you.